Hi, welcome to Allen High School's discussion of thermochemistry at the 10th grade pre-AP or honors chemistry level. We've been talking about bomb calorimetry. Yes, I said the word bomb, and I know all you kids are wondering, when are we going to blow things up in chemistry? Well, for one, I don't have a bomb calorimeter, and two, they don't really blow things up in a bomb calorimeter. Remember from the last video, in a bomb calorimeter, what we did is we combusted material, and we looked at the exchange of heat between the combustion and the water. So here's another example of that. We have a 1 gram sample of our octane, and we're going to burn that, and that burning is going to transfer heat to the water. So we're going to do Q of our combustion process is equal in magnitude but opposite in sign to Q of the water. All right? Now be careful. Again, you're going to be tempted to take that 1 gram sample, but we're doing Q of the water. So we need to do the mass of the water. So we'd have minus 1,200 grams of water times the heat capacity of water, 4.184 joules per gram degrees Celsius. And then its final 33.20 minus initial, which was 25. Again, you notice that your temperature of your surroundings went up. More evidence that this is an exothermic process. And if you did that math, we would get minus 4.117 times 10 to the 4th joules. And I went with 4 sig figs. On this, our final number is going to have 4 sig figs in it, so I just kind of stuck with that. And our temperatures, well, let's not get into the significant figures of temperatures because we haven't learned that till AP Chemistry. So I'm going to just average it out to 4 sig figs because that's what we want in the end. Now, in the last video, I did this in steps for you. Let me show you how we would do this all in one-dimensional analysis. You would take your joules, we're going to do a double unit conversion. You take your joules and you put that per the amount of grams. In this case, it's pretty straightforward. It's per 1 gram. But in the last problem, we could have put it per the 0.303 grams. We could have put that in the denominator. Now, I'm going to convert mass to moles using molar mass. So now my grams cancel. I'd have joules per mole, but the question asked for kilojoules per mole. So the last step is going to be to get rid of joules, go to kilojoules, find your prefix, put the number 1, and then put your scientific notation. Okay? And when we're done, we get minus, don't forget that negative because it's exothermic, 4.704 times 10 to the 3rd kilojoules per mole. Now, personally, I prefer to do it this way. All right, that's my final answer there. I prefer that way, but you can do it in the steps if you want. Just show me all your work. That's what's critical. You got to be able to prove to me how brilliant you are by spewing some of that brilliance onto a piece of paper. Now, the next one's going to be slightly different. It is still a heat transfer process, but now we're going to do it at constant pressure instead of constant volume. And it's going to be kind of open up to the air. We'll do it in class, so I think you'll get a better sense for it. To find the specific heat capacity of metals, this is a common technique. So this time we're not after the heat per se, we're actually looking at that specific heat capacity for our metal, in this case, copper. So the first thing we're going to do is find the heat change of the water. So I'm going to find Q of my water, and it's an MCAT, the same thing we've done before. It's MCAT throughout this problem. Calorimetry is dealing with MCAT. So I'm going to get my water, make sure you get the right mass, not of the copper. I'm doing the heat of the water. So I need my 100 grams of water times the heat capacity of my water And I'm going to look at the temperature change of the water. So my water in the cup starts at roughly room or ambient temperature. Yours in the lab may end up being closer to 22, but that's considered room temperature. So ambient means room temperature. Standard ambient temperature and pressure is 25 degrees Celsius. So we start at 25. That's our initial for our water. And then we're going to go end at 25.35. So we have 25.35 minus 25 degrees Celsius. Now, we're not using this water bath as part of the water part. That's a different stage. That's why I didn't use that 100 degrees here. We have a cup of water at room temperature. We're going to drop our hot copper into it, and the temperature is going to go up. And when you do that algebra, I get 1.46 times 10 squared joules. Now it says determine the heat change of the metal. Easy, easy, easy. Why? Because all of the heat that the metal lost went into the water. We're assuming none of it goes into the calorimeter. So that means that Q, the heat change of our copper lost heat and it went into the water. So it's equal in magnitude but opposite in sign of the water. Now, that's not telling you that one of these is exothermic and one of these is endothermic. All I'm doing here is saying it's equal in magnitude but opposite in sign. All right, so that's all it's going to do is change the sign. And so in this case, that means that the copper is minus 1.46 times 10 squared joules. Okay? Now, the question then says using this heat, so I have minus 1.46 times 10 squared joules, find the specific heat capacity of the metal. So now I'm going to do MCAT again, but this time I have a different unknown. I know my mass of copper, it's 15 grams, but I don't know my specific heat capacity of the copper. Now my copper started at an initial temperature of 100 degrees. We popped it in the water, we left it there long enough for thermal equilibrium to be achieved. That means the temperature is going to transfer until both of them are at the same temperature. And so that's my initial, and this time the final's the same. Okay, the copper and the water, the copper will transfer heat to the water till they're both the same. And I do want to point something out in just a minute. Let me get these numbers down. All right. And when we solve for the specific heat capacity, watch your algebra, I get 0.130 joules. Watch, you got to know these units. It's joules for every gram degrees Celsius. Now, before I leave you with this video, I do want to make a point here. I want you to notice that the water had a much smaller heat change than did the copper. So the change in temperature for the water was much smaller than the change in temperature for the copper. And that's because water has a higher heat capacity than does copper. So it has a greater ability to absorb heat in and of itself without changing water, or exchanging temperature. So if you have, the smaller the heat capacity, the bigger the change in temperature. Okay, we'll explore this more in class. Until then, this is, and I hope that B now stands for beloved chemistry teacher, signing off.